Everyone. So today I'll be telling you about the design of beams, and this will be your fifth module. Okay, here is the problem. Design a simply supported beam of clear span 3.5 meters effectively held laterally throughout the length. The beam is supported on walls of thickness 300 mm and carries a UDL of 10 kilonewton per meter. So here's the given data. It says it is a simply supported beam of clear span is 3.5 meters and it is laterally supported. Okay, and the beam is supported with 300 mm wall and it is carrying the UDL of 10 kilonewton per meter. So the load is 10 kilonewton per meter and the bearing is, it is supported with the wall, right? So bearing is 300 mm and clear span is 3.5 meters. So that means you have a simply supported beam like this and it is carrying an load of 10 kilonewton per meter. It is a UDL load, that is why the unit is kilonewton per meter. Okay, if it is not mentioned UDL also, with the unit you will have to take your values. So that will be 10 kilonewton per meter. Fine. So now we'll calculate the load now. In the load calculation, you need to consider the dead load and also the live loads. So here the load is given as 10 kilonewton per meter. So the very first step is load calculation. In the load calculation, you'll have to take the dead loads as well the live loads here. So here the beam is, if you assume the self weight of the beam as, okay, self weight of beam as anything you can assume 1 or 0.1 or 1 or 1.5 like that. So I will take 0.5 kilonewton per meter. You can also take 1 kilonewton per meter and it is an assumption. Is it fine? So now if here you have the total load. What is the total load? The load is given as 10 kilonewton per meter. If you add the both, you will get it as 10.5 kilonewton per meter. Is it clear? So now here this will be the total load. Okay, so the total load is 10.5 kilonewton per meter. Then we'll factor it now. That's it is WU will be, W is nothing but this. So factored is WU. So that will be 10.5 multiplied by 1.5 is the factor of safety. So that will be 15.75 kilonewton per meter. Okay, so that will be 16 kilonewton per meter. If we round it off, the total load will be 16 kilonewton per meter. So this will be the total load here. And so now we'll calculate the shear force and the bending moment. The next step is calculation of bending moment and shear force. Okay, bending moment and shear force, as we are doing the design problem, you need to calculate the bending moment and shear force and you need to check whether the section is safe for moment and shear forces. Okay, as it is mentioned, it has a simply supported beam. Your simply supported beam is carrying an UDL, means the bending moment equation will be how much? Bending moment will be equal to moment, MU will be equal to, as we are using the moment, WU, that is factored load, moment also will be factored, WL square divided by 8. So W is 16. So here WU L square divided by 8 is the equation, 16 is the load and L will be 3.8. How did you get 3.8? Is CL is equal to 3.5, right? 3.5 plus 0.3 on the either side. 0.3 plus 0.3 divided by 2, that will give you 3.8 meters. So this is L effective. So MU you got it now, WU L square divided by 8. So you got everything. So that will be converted, that you will get it in kilonewton meter. So I'll round off to 30. Now with the shear force equation is VU W UL divided by A, WUL divided by 2, sorry. So this is 2, WL by 2. So 16 into 3.5 divided by 2, you will get something around 28 kilonewtons. So you got to know now the bending moment and shear forces of the section with respect to the loading. So now next we'll calculate it is a section modulus. Okay, with respect to the section modulus also you can choose your section, and also you can calculate the area, and from that also you can choose the section from the steel table, as we have not designed for the angle section, just angle now. Okay, you can choose with the respect to section modulus as you can, and also you can choose with respect to the areas. Okay, so now here ZP. Okay, so ZP you can take it as M divided by Fy into gamma M naught. You can calculate by using this equation. Moment will be Mu. What is Mu? So this will be Mu 30 into 10 raised to 6, and that will convert into Newton mm, and divided by Fy is 250, and that is the assumption, into 1.1. So that will be something around 132 into 10 raised to 3 mm cube. Unit is mm cube. So that means 132 centimeter cube. Am I clear? So now you need to search this particular Z in your steel table, and you need to choose the section. Okay. So now we'll try this section. Okay, and with respect to the Z you need to choose it, and we got it as 132. So here you'll have to choose it slightly higher than that, 145, like that I have chosen. As it is a beam, you need to choose the beam section only, that is the I section. Write down all the values over here: height, breadth, thickness of the flanges and thickness of the web. R1 is the radius, IZZ, and also Z values. So usually you are choosing with respect to the area. Now you are you're choosing with respect to the Z values. Fine. So now we'll go for the next step is section classification. So the next section classification is nothing but you have majorly three types of sections. One is plastic, semi-plastic, and the compact sections. With respect to that, you will have to choose which section you are designing for. That you will get it in page number 18 and table number 2. So here you have the table number 2, and this is in the page number 18. Okay, so the section classification will be something like this. So here I told you, it is a plastic, compact, and the semi-plastic. These are the three types of the sections. Okay, so with respect to that, you will have to choose it. Okay, here you have the rolled steel beam, and the welding section, and the compression due to the bending. Here is the limiting values. So here one thing is you need to remember, and whatever you have seen this will be for the flanges. How you will get to know here? B divided by thickness of the flange, TF. So next here also you will get it for the thickness of the web, TW, and this will be giving you for the web, and this will be giving you for the flanges. Clear? So now this will be giving, this totally will give you for the flanges, and this will give you for the web. Okay, so now here you have breadth of the flange, breadth divided by thickness of the flange. That equation you need to calculate, and you need to check whether you got it as lesser than 9.4 or lesser than 10.5 or lesser than 15.7. So if it is lesser than 9.4, then you can tell it as it is a plastic section. If it is lesser than 10.5 and greater than 9.4, you will tell it as compact section, and it is greater than 10.5 and lesser than 15.7, so then you can tell it as it is a semi compact section. Okay, and if it is more than 15.7, you need to redesign the section. Okay, when you are using the rolled steel section, and B divided by thickness of the flange, TF, if you calculate, if you get more than 15.7, you need to take it as, you need to design it, redesign it. Okay, epsilon you need to calculate here. Okay, so I'll tell you how to calculate epsilon. So this I think it is clear. And here also the same thing. Usually it will be in the if it is the symmetric section, it will be neutral axis will be in the middle of the section. B divided by TW, if you get it as 8.84 epsilon, 105 epsilon and 126 epsilon. If it is more than this, you need to redesign it. That is what the concept is. So it is a limiting one, and all this other values is for the angle sections, and if it is negative or positive, it depends on the symmetricity. Okay, symmetric. If it is unsymmetric or anything. Am I clear? So now we'll design this. Now I'll tell you how to design it now. So classification of the section. So here first we will find out what is epsilon here. Epsilon is nothing but, you can calculate, you are already familiar with this, F 250 divided by Fy. 250 is nothing but Fy. Fy value is 250, that is equal to 1. So epsilon is 1 here. So now we will calculate B is equal to, so that is BF divided by 2. Why B is equal to BF divided by 2 is nothing but, whenever you are taking the I section over here, this I section is the breadth. B represents, it is the half of the flanges. Okay, so that is, you are got an I section here. So B is nothing but from here till here. So this is B. Okay, so what is this now? Breadth of the flange, BF. So the total height is how much? Small h is like this. So thickness of the flange is nothing but, thickness of the flange is this one, thickness of the flange. Okay, and the R is R. If you have a circle over here, it is not a straight line like this. This is R. Radius of this curve is an R. Okay, so this is R. So now where the end R ends, circular portion ends, from there till here, that is D. This will take it as D. Where the circular portion ends, from here, that is the very straight portion of the angle web portion, that we will take it as D. Breadth is nothing but half of the breadth of the flange, that is B. B is equal to breadth of the flange divided by 2. Okay, so what is 90 divided by 2? Correct, so it is 45. Now we will calculate here. So B divided by thickness of the flange. Why I am taking the first one is, it is a rolled steel section. Always the I section will be a rolled steel section, right? So it is a B divided by thickness of the flange. You need to take the I section as a rolled steel section, B divided by thickness of the flange. Now we will calculate B by TF, so that you can compare it between 9.4 or 10.5 or 15.7. We'll see how it is, how it will go on. So now we got what is B now. Okay, so B divided by, what we need to calculate? B divided by thickness of the flange. So what is B now? 45, right? 45 divided by thickness of the flange is 8.6. Just now you took it, no? 8.6. You will get all this in the steel table, and that is how much you will get it, something around 5.23, and again it is lesser than 9.4. So if it is lesser than 9.4, what is our answer? It is a plastic section. Okay, if it is greater than 9.4 and lesser than 10.5, it could have been a compact or semi-compact, depends on the values. Okay, now it is a, what is that? It is a plastic. Okay, so now here you got the answer. Now it is a 9.4. Next, we'll go for the T divided by thickness of the web. It is for the flanges. Flanges we calculated. Now we'll calculate it for the web. D divided by thickness of the web. How do you calculate D? What is D here? It is the curve portion, we need to neglect it here. Only the straight portion, you can name it as D here. So what is D here now? So height, in the total height, if I minus 2 times of thickness of the flange plus R, correct? So here you have thickness of the flange plus r. I will add these and add this. In total I'll minus these two parts. So that is why it is 2 multiply by 2. So that will be 137.8 mm. Okay, in the total 175 it will be 137. Height is how much? H will be H is 175. Okay, so what is D now? 137.8 divided by 5.5. Thickness of the web is 5.5. So that you will get something around 25.05, and that is lesser than 84 epsilon. So if you see it here, it is a symmetric section, the neutral axis at the middle. Okay, so you need to take this condition. D divided by TW, if you calculate, it is lesser than 84 epsilon. 84 epsilon is nothing but plastic. So what is our conclusion now? So you need to conclude it as therefore hence the section is plastic section. Okay, hence the section is plastic section. Okay, so this will be your conclusion. Okay, next step we will have to check for shear strength, and you need to check it for moment. So here is the shear strength. First we will take it, and that you will get it in the page number 59, and the clause number is 8.4. Okay, so if you go in the page number 59 and the clause number is 8.4, you will get it here shear, and V is, it should be lesser than or equal to VD. V should be lesser than VD here. VD is nothing but design strength. VD you will get it from Vn divided by gamma m naught. Gamma m naught, as you know, it is a partial safety factor, and if you want, Vn is nothing but Vn is equal to Vp. How do you calculate Vp? Av Fy divided by square root of 3. That means Vp is nothing but Vn. If you substitute it here, divided by gamma m naught, you will get. Okay, same thing, we'll write it down here. So what is V? We calculated, no? So that is V is 28 kilonewtons, and always V should be lesser than or equal to VD. How do you calculate VD? This is our check actually. We need to check whether it is correct, this equation is correct or not. Okay, so now we'll calculate what is VD here. VD is nothing but Vn divided by gamma m naught, correct? So that will be equal to Av Fy divided by square root of 3 into gamma m naught. Okay, so that is Av is nothing but H into Av is nothing but shear area. Shear area always will be with respect to the web. Okay, shear will happen usually with respect to the web, as it is a thickness is less, and that will be the force which is taking at the laterally. So the H, total height into thickness of the web, you need to multiply into Fy divided by square root of 3 into gamma m naught. So that you will get it as 175 into 5.5 into 250. Gamma Fy is 250 divided by square root of 3 into gamma m naught is 1.1, and that will convert into kilonewton directly by multiplying 1000 in the denominator. So you will get it as 126.3 kilonewtons. Okay, and this is greater than 28 kilonewtons. Okay, so V is how much? 28, and this should be V should be lesser than the designed shear force. So it can take up 162, but it is applying 38, so it is safe. Okay, so you can name therefore safe. Okay, next we'll go for the check for design moment capacity. So now P is in the page number 53, you will get it is in the clause number 8.2.1.2. Okay, if you see it is in page number 52, here you have M should be lesser than MD. Okay, so MD is nothing but design momentum. So here you have in 8.2.1.2, here you have MD is equal to beta B ZP Fy divided by gamma M naught. Beta B is nothing but it will depends on plastic compact or semi compact section. Okay, ZP, I'll show you how do you get that is ZP Fy and gamma M naught. So that should be lesser than 1.2 if it is in the case of simply supported, or 1.5 ZE that it in case of cantilever. This is your check. Now we'll go for the check it for our problem. So what is M? M is, that should be lesser than or equal to MD. Now we'll calculate what is MD here. MD is equal to, so how much you will get? MD is equal to beta B ZP Fy divided by gamma M naught. Okay, so beta B is nothing but it is 1 into ZP. Okay, I'll tell you what is ZP. 250 divided by gamma M naught is 1.1. ZP is nothing but you will get it in, it will not get in your steel table, you will get it in your IS 800 only. Okay, if you open the page number 139, okay, it is in page number 139. See here, it is in page number 139. So here is ISMP 175, that is what we have designed. 175, if you go through it, you will get it as 166.08, that is ZP. That you will get it here 166.08. So 166.08, okay, that into 10 raised to 3, okay. So that you will get it as 37.75 kilonewton meter. Okay, so if you take it as into 10 raised to 3, that will convert into kilonewton meter. Okay, and what is M here? M is 30. So 37.75 is greater than 30 kilonewton meter. So it is safe. Okay, so we have done with the shear and also we have done with the moment check. So it is safe now, and finally we'll have to check for deflection. Okay, we'll check for deflection now. So if you open page number 31, table number 6, here you have the table. Vertical load is applied, okay, and it is a simply supported span. Here you have two things, elastic and the brittle. Concrete is a brittle material. Span divided by 300 is the limit. Take down that is the allowable limit of the deflection. Okay, so W, it is how much? 10, right? Only the load applied is 10 kilonewton meter, and also you can write it in Newton per mm. Okay, so now we'll calculate the deflection. So if it is a W simply supported beam, and what is W deflection equation? W L power 4 divided by 384 EI. That you have already derived this in your this one elements, I think. So it should not be greater than allowable. Okay, so that is what the equation is. So here is how much? L divided by 300. So what is L now? 3800 divided by 300, so that will be 12.67 mm. Okay, so now we'll calculate what is calculated deflection. So it is 5 into W is 10 into L is 3800 divided by 384 into E is 2 into 10 raised to 5 Young's modulus E into IZZ. You will get it in your steel table, 1272 into 10 raised to 4. 10.67 something you will get, and that is lesser than 12.67. Allowable is, according to the code book, is 12.64, and whatever we are designed is 10.67. It is a maximum limit. So it is safe. It should always be lesser than the allowable one. So therefore safe. So here also for deflection also it is safe now. Okay. So now next we will calculate it for last check is. So finally you need to check for web buckling and web crippling. So here it is web buckling of the support. So here it is the buckling forces will act like this. So if it is in the support, so in the buckling here it says in the code book says it is a 45 degrees if it is dissipating. Okay. And then it will be something like this. Okay, it is an assumption and it is also in the code book. So now here from here this distance of bearing will take it as b1, and the distance of this after the buckling forces at the support failure plane, it will be in the distance of n1. Okay, so if you go it in the page number 67, here you have the web check. Okay, here you have the equation b1 plus n1 into tw, and also you need to multiply with the fc value. Okay, fc value equation does not here, you need to by heart it. Okay, so now we'll write that equation now. Okay, so this is how you'll calculate. So fcd is equal to b1 plus n1 into tw into fc, and that should be not lesser than v, that is the shear forces. And for that we want an fc value. Here for that we need to calculate kl divided by r. So first kl you can calculate by using this equation, so that you will get 60.4. So to calculate fc you have you got it as kl by r as KL as 60.4, KL by R as 60.4. So now FY is nothing but 250, right? So if you go for the page number table number 9C, so you will get it as 60.4. In that if you choose it, you will get it for as 168 like that, and 168 and 152. Interpolate between these two values, you will get it as 167.36 Newton per mm square, then that is FC. So you got to know now what is FC, right? So now we'll calculate what is N1. What is N1 here? H divided by 2. Why? It is the inclination is 45 degrees. Right? So inclination is 45 means here if it is a 45 degrees, so it will be same. This side also it will be same, and the height also it will be same. So what is this height now? H. The total is height is H. So H divided by 2. Fine. So that you will get it as what is n. This is also same and this will also be same. Yes, it is the angle is 45 degrees. So write down everything. H will be now what H will be. So 175 divided by 2. So H is 175. So it divided by 2 you will get N1. So N1 is 87.5 mm. Okay, so now you will substitute everything here, so that you will get FCDW value, and that should be compared with V. So now we'll substitute. B is, I'll take it as bearing as 80. You can also assume it as an 100, and whatever the bearing is given, complete bearing we cannot give 100 or 150 or 200, like that you can assume. This is an assumption. 80 bearing B1. Okay, plus 87.5 is N1. Okay, and multiply by thickness of the web is 5.5 into FC is 167.36, and that divided by 1000, it will convert into kilonewtons. 154.18 kilonewton, and that is greater than 28 kilonewton, so it is safe. So it is safe for buckling. Now we'll find out finally for crippling. Crippling is nothing but if it is the I section is like this. Okay, so it will cripple like this. Okay, so it is like this, failure of the web in this in this manner. So this we call it as in crippling. Okay, so how to calculate this is check for last check is check for crippling. Web crippling. Okay, So again you will get it in the page number 67, clause number 8.7.4. The same clause, same page number, you will get this. So crippling is, so that Fw is nothing but B1 plus N2 into Tw into Fy divided by gamma m naught. Okay, and that should not be lesser than V. See here, B1 plus N2 divided into Tw into Fy divided by gamma m naught. This will be the equation, and B1 is bearing, and N1 N2 is nothing but you can calculate by using the slope as 1 is to 20, 1 is to 25. That clause is given here. How do you calculate that? Okay, so here it is given as 1 is to 20, 2.5 of the plane of the flanges and the Tw and Fy. So I will calculate it. See here, so this is how the crippling will happen. Crippling will be at the next to your support, that is joint. Okay, so that it will be N2 will be in the distance of from here till this way. Okay, so that means when it reaches the critical axis. So the critical axis is in ratio of 1 is to 25. So 1 is to 25, 2.5, sorry, 1 is to 2.5. So if you draw the line, that axis will be in the uh, distance of r1. R1 is the radius and thickness of the flange. Thickness of the flange plus r1, that will be the critical axis. So that ratio is 1 is to 2.5. And from here till here the distance is n2 and this distance is b1. The height is h. Clear? So now we'll calculate how do we get that. Okay, so now what is n2 here? N2 is nothing but 2.5, okay, into thickness of the flange plus r, that is ratio, this one. So how do you calculate this one? You know this distance, that is ratio 2.5. 2.5 times of r1 plus thickness of the flange, you will get this distance. So that you will get 2.5 into 8.6 plus 10. So that is 47.5 mm. Okay, so you got to know what is R2 now, and we have already taken what is BS. You can also, this is an assumption, you can take 100 and 150, whatever you want. Okay, into how much? 5.5 into 250. This is 7, that is okay. So divided by 1.1 into 1000, so that 158.12 kilonewtons, and that is greater than 28 kilonewton, so it is safe, therefore it is safe. Finally you will have to conclude it as therefore provide so it is safe for all the check. ISMB 175 at 0.3 kg per meter as beam. Okay, so this is about the design and check of the beam. Okay, thank you.